it was very common for teachers to give summer homework, which, yeah, I think now looking back, I feel they shouldn't give it. That's it. That's not appropriate. Or I would like my spring break to be clean, no more, no extra load. Thinking of writing to the CTE, what is it, Communication and Technology Excellence, so that we can request for a camera. I've done that 2 times before, so they have a proper, like, professional camera, which you can press a button and it starts recording and everything is there in the university system. So that'd be nice, so. I've requested it, it's not that they're against it, they appreciate it, but it's just usually in a university budget. They have ways of distributing the money, so they say you at least have a camera, there are other places who don't even have a camera, so first we will invest on that and then come back to this. So.
Weird system.
I would think it's reasonable to say that when you don't have a camera in another department, we will first invest on that and then come back. So I don't have anything against that argument. But now I'm going to argue that this camera is giving up. Like,
Even they allow you, it will get around 5-6 months for that.
yeah, I don't mind that.
That's
As
why
far
I
as
think that one
they,
is
as far
around.
as they decide. The only problem is that it's very expensive on the university to put a camera, like, even though it is about $1,000 for the camera, so by the time they put everything, like, just the labor cost and other things. They have to worry about 10 years down the line. So it costs, I'll be surprised, $10,000 to $20,000 by the time this has to be put up on the roof. So that's just the way system works. Like, their liabilities are bigger, maybe that's the way to put it. Okay. Okay, so
You make it bigger.
bigger, yes, thank you for reminding. For some reason, don't have that habit. Even the YouTube videos, I watch it this tiny. And then my wife will come and say that, how do you want to watch that? You should make it bigger, so. It's just a habit, yeah. Okay, so this is. Yeah, can torque be measured in joules? What's the internet say?
Yeah, it said if we measure in joule, that will be like a force energy. That joule is
So it's
energy.
not okay?
Yeah, that's why mathematically okay, but in physically not okay. I found that. I don't know. I found that one is really.
Why maybe one talks about.
Because one is that product and cross product.
Well, the units, when we work out the units are the same. A paradox.
Not really, I think it's, yeah, I don't know. I feel if there's nothing wrong in using it. Can you think of any other thing that has two different physical quantities that have the same units?
Same.
That's reasonable. If torque is measured in joules, we might get confused, so that's reasonable. Could be confusing, but nothing wrong, I guess. So come up with two physical quantities that have the same units. Where's one? Think of surface tension as a hint. I'm pretty sure there are more. Something that comes to my mind immediately is surface tension, and I'll let you guys fill in. There's a homework 6 that is due March 19. Midterm. I think the midterm will be classroom exam. It won't be at home like exactly like earlier. That's what I'm thinking of. So, or at least as of today, that is what is sleep changing. Last time we started spherical pendulums. Let's try to do this. So the idea here is that we are doing Lagrangian, and if you notice, very simplistically speaking, we have Newton's law. And Lagrangian mechanics, or the action principle, is nothing but restatement of Newton's law. But then somewhere in between, I have also told that not all forces can be accommodated in a Lagrangian. What are the forces that cannot be? Tension and normal force and so on, or non-conservative forces. You need a potential energy to write the Lagrangian. You need the potential energy, and potential energy is not available for every force. So it seems like Lagrangian is very very limited in applications.
Yeah.
Maybe that's the way to put it. And I also said that now maybe sometimes you can do certain things and try to get the effect of other forces nevertheless. So that's what we want to see today. This is broadly called Lagrange multipliers. Even if it's a non-conservative force, like normal force is a classic example, we can try to get some information about it. So let me try to write this down. So first, I mean, just as a strategy, so we have Newton's law. So F. I like to write Newton's law the opposite way. So I can write it as a sum. So mass times acceleration is equal to F1 plus F2 plus so on. So that many forces that could be acting on it. And it also introduces the idea of, so there is a conservative force. There are many relations that can be used to define conservative force. One of them is that the force is negative gradient of potential energy. Like the idea is that there exists a potential energy. Lagrangian, or the action principle. Lagrangian is kinetic energy, K, minus the potential energy. So the way the very statement of the Lagrangian is that you need a potential energy. If you don't have a potential energy, you will be stuck right here at the first step. You won't be able to write the Lagrangian. You won't be able to do too much. Let's also think of when we say conservative forces, let's think of at least few of the forces that we come across. So there is gravity. There is normal force. There's a force of tension. There are some special forces, and there is force of friction. Maybe drag. These are some of the early basic forces that you introduce in Newton's laws to accommodate for simple studies. If a mass is moving, a car is moving, usually you can play around with this equation. If you notice, gravity has an expression for the force, F is equal to mg. Now, if I were to ask you how do you write normal force? Like the moment I say, what is the gravitational force? You have an answer. Oh, it is mg. And so basically it has a magnitude and a direction. Direction is towards the center of Earth. And mg is an expression that's related to the two masses of the objects we are talking about, the distance between them. What about the normal force? And you will realize that, oh, we never write the expression for the normal force, right? But we know the direction of the normal force, correct? So direction is of the normal force
Opposite plane of.
of opposite to the?
To the weight.
No, that's not correct.
opposite
Give me a situation where it is not opposite to the direction of weight.
Oh, yeah, the inclined plane.
Inclined plane, or now there is a normal force, I'm touching it. The normal force is horizontal, right? It doesn't have to be, nothing to do with gravity. It has no reference to gravity, surface, right? It has something to do with surface. So what's the direction of the normal force? Perpendicular to the
Surface.
surface, not the applied force, right? It has nothing to do with the applied force. It is a surface. If I touch this surface, it's perpendicular, it will be in this direction. The floor is flat, so it is perpendicular to the surface. If you tilt the floor, the normal force tilts. Okay, so it is the surface that decides, it's perpendicular, normal to the surface. So we know the direction for this. Normal to surface. Magnitude. So what is the magnitude of the normal force? We never write down, but nevertheless, you can use Newton's law to capture the normal force in terms of other forces. For example, as some of you were pointing out, if there is this remote control sitting on this box, right? Gravity is acting downward, normal force is acting upward, it is equal, right? If I were to push on this remote control, does the normal force increase or decrease if I push it downwards? It increases, right? Because now it has to balance not only the gravity, it has to balance my force too. If I were to lift it a little, like if I were to lift it a little, not lift it means it should not lose contact. Before it loses contact, if I were to try to pretend to lift it up, then it will decrease. Normal force is decreasing, and the moment it loses contact, it goes to zero, right? Normal force is zero immediately, right after it loses contact.
There's a normal force on your hand.
That's good. So that you can say it's a tension or normal force. Very good. Yeah. So there is a normal force in the hand. Exactly. Very good. So it seems like one could argue that normal force is not really there to, it's not having an expression. It is only sort of cheating in the sense that whatever force we cannot accommodate for, you're just putting it in the normal force. That's a very loose statement. I wouldn't say, I would not put anything to saying that it is a cheat
It's
force,
already-
but nevertheless, it tries to compensate. So what is it trying to compensate? Its idea is that it has to stay on the surface. There is a constraint that it has to sit there, right? It cannot move up. Right? The remote cannot start flying. That has to be decided by some force. So mg is acting down, it should go down. If the normal force is too big, it will go up. So it is just balancing the force that is acting on it. So in that sense, normal force is contributing to putting the constraints. So it constrains. It is putting a constraint on the mass. It helps. Direction is decided, is decided by the surface. But what is it doing? It is making sure that the object doesn't do anything counterintuitive. It doesn't fly, it doesn't leave the surface, it doesn't go into the surface either. Right? So it is making sure that it is staying at a point. So that's what I mean by constraint. Let's look at the tension. What's the direction of the tension? What's the direction of the force of tension? Let's say there is a string. It is always along the string, right? If a mass is hanging onto it, the tension, the rope decides in which direction it's going to pull it. Like even though the mass is hanging vertically down, if you were to have the rope in this direction, the force you will apply, the force that's acting on that mass is in this direction. So this is a way to guide your force if you want from one point to the other. So direction is along the string. And what about the magnitude? Again, it's a constraint, correct? You don't, it is making sure that it is at the tip of the string. Like if I have another mass pulling onto it, it makes sure that it is staying there. Like it stays at a certain point based on the motion of the object. So this is also is decided by a constraint. And friction, let's think of friction when it is rolling. There is a kinetic and static friction, but let's think of rolling when a wheel is rolling. That's your wheel rolling, and that's there is a omega here, and there is a v here, right? So you usually learn that there is a coefficient of static friction, coefficient of kinetic friction, right? So that means there is a force of static friction and force of kinetic friction. When things are moving, it is the force of kinetic friction that comes in. When something is static, it is a force of static friction. In this case, be careful of what I'm asking. So that is mu Sn, mu Kn. There are two forces that could apply, and be careful with the language I'm asking. Which of these two quantities decide on the force acting on a wheel?
If it's perfectly rolling,
It is perfectly rolling, let us say. Good. Yeah, that's a good statement. I should clarify. If it is perfectly rolling, that means it is in touch with the surface at every instant, and which means that at that particular point, it is at rest, right? And what's the velocity of this point with respect to this? It is zero. So if it is at rest, you would say it is static force. But now answer my question. So that's very good. So that we have reached this. Which of these two quantities acts here?
static friction, coefficient static.
It's a static friction, yes, but is it this? Is the force acting on it mu s times n?
Using that relative to point, so that would be what's supplying traction.
Let's say this was 30 newtons. what's the force of friction acting in here? Let us say it is about front or to the back.
B,
Is it 30 newtons? Something less than 30 newtons. That's very good because it has to be less than or equal to. Unless I reach a threshold. So for example, if there is a remote again, if all of you guys can see it. If I were to push on this, what's the force of static friction acting? It is not moving.
The force you apply.
It is supposed to be.
Force you apply.
I cannot hear.
The force you apply.
It is equal to the force you apply, but it is not equal to mu s times n. And mu s times n is only applicable when it starts moving, or right when it is moving. That means I have crossed a threshold.
the maximum.
So it's a maximum value you can apply. So here, there is a force of friction, which we don't know whether it is backward or forward as far as the static. Whatever is that, let's say it is forward direction, we don't know that, force of friction. We can only say it is less than or equal to mu s n. So that is all we can say. Nevertheless, this force of friction moves, makes things move. Let's say it is perfectly rolling. There is a constraint, so perfect rolling involves a constraint, right? So, and the constraint is S is equal to theta times R. So amount of rolling does it do, amount of angle that the wheel rotates is exactly equal to theta times R of the amount that it goes forward. And this leads to the idea that V is equal to omega times R. These are constraints. So this is a constraint. That means to say that the linear kinetic energy decides my rotational kinetic energy. If I know how fast it is moving, I know how fast it is rotating too. It might be a factor of, in the sense that moment of inertia is not exactly the same. Right? So in that sense, it might be very different, but nevertheless, this is a constraint that uses. Notice all what is common in all this is there is a constraint. Right, something most of the time we know the direction, we can decide on the direction, but we don't know the constraint. And we want to learn how to introduce these quantities. These forces do not have potential energies associated with them. Nevertheless, we want to write a Lagrangian for this. Okay? So that's what it will be. So let's take the example of a spherical pendulum. Maybe I can go to the next. Any questions associated with it? So the example I'm going to have is spherical. Maybe I should even before going there, I can give you the answer. Go back. So very broadly speaking, we are going to say Lagrangian is equal to the kinetic energy minus the potential energy. Okay. And I want to accommodate for this. There is no potential energy for these forces. But I will do it anyway. This is how we will do it in a very simple way. Plus, right? It is plus because potential energy is negative of the work done, remember, right? So this is taking care of that plus. So let's say it is a normal force. I want the normal force coming in. It has to be a scalar. So normal force is a vector. I have to build a scalar out of it. I will take a dot product because I want to build a scalar. And I know something very clearly about the normal force, that it is perpendicular to the surface. Which mathematical quantity picks the perpendicular to a surface? If I ask you, give you a complicated geometry, let's say ellipse, and ask you, no,
Oh, that's between two vectors.
no. If I give you a surface, complicated surface, 5, right? some random surface
the
like
surface now.
parabolic, like XYZ, right? Some function I give you, that's a scalar function. And I ask you, give me the normal vector at a particular point on the surface.
Surface interval.
Like, let's say this is a sphere, right? A sphere, what is the equation of a surface of a sphere? It is r square, like let's say x square plus y square plus z square is equal to r square, right? That's the equation of a sphere. Now I say that no, I'm interested. This is if the origin is at the center, right? I say I'm interested in this. I want this vector as a derivation. I know that it is radially outward. The answer I know. At this, I give you this point and I ask you, give me this vector, the direction. What's a general principle? So how would you go around finding it out? Think electrostatics,
Right.
equipotential surfaces and electric fields.
Surface
Very
interval.
good. Yeah, so gradient is the answer. Notice electric field lines, if you think of, these are electric field lines. Right, they are perpendicular to equipotential surfaces. How is the electric field related to the electric potential? What's the connection? Electric field and electric potential? Perpendicular to each other, very good, but what's the relation? Mathematical relation. Minus del gradient, minus of gradient of the potential V, right? You write V, but in these courses we write phi, right? Somewhere we switch from V to phi. Gradient of phi gives you the electric field, negative because we are talking about force and potential energy. Same thing with force. Force is gradient of potential energy, perpendicular to the constant energy surface. It tries to minimize energy. It goes from one surface that has uniform energy to the next surface, right? It's perpendicular. So any surface you give me, if I operate the gradient, that gives me the perpendicular direction to it. And then you have to normalize it and do those things. So whenever you want to think of gradient, think of normal. That's the best way to have a geometric picture. Like scalar product, you think of angles, right? If you have two vectors, scalar product, angles. Cross product, what do you associate cross product with?
Two vectors.
Two vectors, yes.
Finding.
Area.
Yeah.
At least one of them. There are many interpretations you get. The area of the parallelogram that you construct out of the two vectors, that's cross product. Gradient is the next thing you come up in vector calculus. Gradient is the normal to a surface, like normal to the potential that you act on. That's your surface and that's the quantity. So you would say this is gradient of, I want to build an equation out of this. So you say this is x squared plus y squared plus z squared minus r squared. Right? This is a vector now. This vector will be always perpendicular to this sphere. If you write the equation of an ellipse, take the gradient, it will give you the normal to the ellipse. And at any point, pick your favorite surface, it will always do that. In that sense, it's a very strong tool in a sense. Okay. With me? Okay, so all that was a digression. I wanted to accommodate non-conservative forces, even though Lagrangian is in principle meant for conservative forces. I take the normal force. I want to dot it with something. That means to say that I want to say that normal force is in a particular direction, but it's in the direction of normal to the surface. So I put the gradient there. Right? And then I need a surface that is a constraint, right? Constraint is most often, if you have the choice, constraint can be various ways. At least for the normal force, typically the constraint is for it to keep it on a surface. Like a pendulum is swinging on a sphere, right? The tension force is making sure that it is on the surface of a sphere. So you put in the equation of a sphere, right? So this is a surface, equation of surface. that's the idea we will go with. Okay, how do you accommodate non-conservative forces? Put in the normal force, put in a gradient in front, and then the equation of surface. So this is not applicable for every possible non-conservative force, but at least some certain set of forces. These are called forces associated with holonomic constraints. So these are called holonomic constraints. If you can do this, they're called holonomic constraint. The definition is a little more precise than that, that you can write differential form for that, but overall, our idea would be this. Notice the way I have defined you the equation of surface, it was x square plus, in this case, it will be x square plus what? For a sphere, it will be minus r squared, right? That's an equation of a surface. This will give me a perpendicular. If I divide by 2, it's also an equation of a surface, the same equation of the surface, it will give you the same direction. My magnitude will be off, but it'll give you the same direction. I can write 77, any arbitrary number, still it will give the same direction. So you are off by a direction, right? So generally what you write is, you don't write the normal force there, you say that's a lambda there. Because it is not really the normal force, it could be off by a number. Right? It will be off by 3 or 77 that I wrote there, we don't know. And that's called the Lagrangian multiplier.
Your function or vector or
It-
scalar.
Yeah, most of the time when we are working, either it's a vector or a scalar. Often scalar, if you're doing exam problems, I try to give you scalar quantities. But in the example that I will do here, I will do it for a vector, I'll do it for the normal force. So how we will work with this as an application tool, get the equation of surface, take the gradient to begin with, and dot it with a vector. That's the term you will add to the Lagrange. Okay, so that's how we will work. So let's go to the spherical pendulum and see how this works. Any questions at this stage? The strategy? Existing kinetic energy plus potential energy, non-conservative force, right, with some number attached to that scale, times the gradient of the equation of surface. Okay, so that's our new Lagrange. So let's do a spherical pendulum. And what's the kinetic energy for a spherical pendulum? So again, spherical pendulum, this is the rooftop or ceiling, let's say, and that's your mass m. Let's say this is a square, the length of the pendulum is a instead of r, and this could be the angle theta. And what's the kinetic energy for this? This is half m, and I say it's v dotted with v in 3 dimensions. It's velocity dotted with velocity. Generalized coordinates probably is so theta and phi, right? So we are having both dimensions allowed here. It can come out of the board also. It doesn't have to stay in the board. Phi will be the direction that's coming out of the board, latitude and longitude. Okay? But kinetic energy is half mv squared, right? There are how many forces acting on this? On this mass? How many forces? Two. Force of tension and gravity. Anything else you can think of? Mg. Force of tension. Anything else? It can go in a circle, yeah. So this can go maybe if I were to. How many forces acting on? How many say there are only two forces, mg plus g, there is nothing else? There anyone who said that?
Such a force, that's a pseudo force.
Anyone wants to confidently say that only two forces? Huh? Two forces. Yes, there are only two forces acting on, to be confident, so, and that is actually, I mean, believe it or not, when you're in a new investigation, like most of the time we are doing textbook problems, homework problems. There we are confident of there are only two forces. If you are in an unknown territory, we don't know whether there is a force or not. For example, dark energy and dark matter are very very mysterious concepts. Now I can ask, is there any other force acting on our system, on our Earth? We don't know. Right, so that, yeah, maybe, yes, exactly, we don't know, so that's confusion is the difference between a research problem and a homework problem. A homework problem, usually you know the solution, you know that the solution exists, and that changes everything. Just the fact that you know the solution. The moment I remove that confusion, for example, I asked you, is there a third force acting on it? That confidence is lost a little bit, right? So if you have the confidence, immediately you can proceed and do 100 things about it. But that confusion spoils everything. Okay, so there are only two forces, so mg and g, potential energy for it, there is only, so there are two forces. So there is mg, but the mg is conservative, so it has a potential energy associated with it, and we will write it as, what is mg? H, right? Mg H, but we will write it as mg dotted with r. Right, and is that correct? Sign wise?
Unless if you indicate going down, it's positive. Indicate the direction on the board.
So I think mg dotted with r, like think of any direction, right? Random direction, so that's my g. Right? Some weird coordinate system, and that's my r, right? And potential energy decreases along the direction of g or increases along the direction of, that's something we can talk about. Like when you go in the direction of g, you're going towards negative, so this is lower potential energy, that's higher. Right? Higher should give you a positive number, right? So there is this angle theta that's coming in here. So it is mg cosine theta, correct? And this should be a negative number, that should be a positive number, right? So smaller angle, so as theta goes to 0, it has to be a lower number at least, it doesn't have to be negative, and we're going to the extreme where it is negative. So it seems like it should be minus, right? Is that clear, the argument I gave? So it has to be minus.
Lower minus.
Think about it, if I'm wrong, correct me. I think that was the argument I could come up with, which is coordinate independent. We are always used to thinking downwards, right? But what if you're in a place where you don't have the choice to pick it to be in the downward direction? Then it is, I think it's minus in here. That's a conservative force. Now I have a force of tension also, and now we don't just use potential energy. Now I need a term which is force of tension, which is Lagrange multiplier, let's say, right? Yeah, let's write it as Lagrange multiplier, lambda, which is probably T itself plus some constant number dotted with the divergence of gradient or gradient, yes, divergence of gradient operator, so yeah. Yeah, it should be gradient of, sorry, yeah. So gradient of a surface equation. What's the equation? This is constrained to move on a sphere. So it is x square plus y square plus z square minus a square, but I want to write everything in terms of a coordinate independent thing. R, vector R, not referencing into any coordinate system. It is R dotted with R, x square plus y square plus z square minus a square. I have the freedom to put in any number I want to after this. I'll put a factor of half so that lambda comes out to be t. If I don't put this factor of 2, then lambda will be 2 times t. Is that clear why I put that half? No. Let me remove that half. How about that? Huh? No, my point is that I said earlier here that when I set this up, this is also an equation of a surface. 1/2 is also an equation of a surface. 77/2 is also an equation of the same surface. If I do this, it disturbs my factor. If I put 77 here, I have to put a 1/77 there. Right, so I don't know what that is. So that's why you call it a Lagrange multiplier. You don't say this is the force of tension because you don't know that factor of 2 or 3 or 4 or 5. I know because from since I've worked on this problem before, I know that the factor of 2 will really make this the force of tension. But let me not cheat. Okay, so I'm not going to put that 2, so this is not really going to be the force of tension. It will be either a half or a 2 times. Is that clear? That's because of this arbitrary. So that's my Lagrangian now. So we do this. So Lagrangian is what are the dynamical variables? It is just R. Right? And it's R dot, we say it's velocity, right? So this is velocity is equal to R dot. So dr by dt. That's a short form for that, but I like to write it as V. In general, it can be time dependent, but in this problem, it turns out it is not time dependent. Okay, in general, that would be R, velocity, and a time dependence in there. In this case, the whole system is conserved. There's only gravity acting on it. There's no one putting in energy in. So that's your Lagrangian. That's your K minus U. That's the standard definition of the Lagrangian. But now we are going to accommodate for this force of tension, and it is going to be plus T. No, lambda. Lambda. So lambda times the gradient of R. I can do this in 2 ways. I can keep it as it is and proceed, but this can be evaluated immediately. How much is this equal to? So let's do that here. Gradient of R dotted with R minus a square. What is that equal to?
R.
Very good. Yeah, so try again. It is R, yes. Yeah, but something more. Yeah, okay.
This one.
Yeah, you're correct. Very good, very good. So that's I was not expecting such an immediate answer, but there is one. So this can act on this R and that R, right? That's my point. So this acts on one of the R's, very good, right? But it can also act on the other R, right? So if I were to call this R1 and R2 for a moment, I can call it R2, R1. So let's say this is R1, R2, right? But R1 and R2 are the same. That's for temporarily I'm not doing this. I can also say this is R2 times R1, right? So there are 2 of them. So and then I remove it. Is that clear? So there are 2 times it is hitting, and it can also hit on a square. Right? What is a square? Gradient of a square? Very good. So that's 0. Right? And as Nahida pointed out, very good. Then this is 1, right? That's something I have been trying to promote it right from math methods class. So gradient of a vector, coordinate vector is 1. So that's 1 times r. And this is also 1 divided with r. 1 times r is r itself, so it's 2 times r. But nevertheless, very good. It is so it is factor of 2 because there is a 2. I would have written that half just to cancel that 2. Earlier I was doing that division by 2, then it wouldn't have had that. So I was overseeing or foreseeing this factor of 2 that is coming. Is that clear, that algebra?
Why don't we solve the dot product before?
X square plus y square plus z square?
R dot r is r square, can we get it?
Oh, yeah, that's also good. Okay, very good. So this is also equal to r square minus a square, right? Very good, right? That's equal to 2 times gradient, 2 times r times gradient of r. Now tell me, what is this equal to?
This,
No,
no, this R had over R.
this is a vector r. This is the magnitude of the r. There's a difference. What's the difference? That it's a unit vector. Very good. So this is so the only 2 things that we need to know when we're doing vector calculus is, one is that this is equal to 1, and if it is acting on a magnitude, it is r hat. Notice this is not in coordinate like rectangular coordinates, spherical coordinates, cylindrical coordinates, it doesn't matter. It is coordinate independent statements. Those who have not done math methods, this might be slightly new, but think about it and try to learn. So it's okay if you're not seeing this book. This is r hat, so that's 2 times r times r hat. Are they the same? They are exactly the same. So very good, right? So good question as to why couldn't you do this before? It gives you the same answer. Okay. So for simplicity, we will do this immediately, right? So this is equal to half m v dotted with v minus mg dotted with r. Right? No, oh, sorry. This is plus, right? Because u is minus, it becomes the plus. And this one kind of takes away some details of the concept when you do this beforehand. But at the same time, since it's a first example, it gives you more insight in our more clarity. There's less clutter. And it is lambda 2 times, right? 2 times lambda dotted with r. That's it. That's the Lagrange piece. Now. So that's a new piece. And this is called the Lagrange multiplier. And now we do everything the same old method. Once you have the Lagrangian, what do? We do the canonical momentum, right? So this is canonical momentum. The derivative with r, derivative with velocity, right? So this is canonical momentum is dl by dv. What is that equal to? And then you say canonical force or generalized force, right? Canonical, yeah, why not canonical force? I changed my, I think yesterday or last time I wrote generalized force, but I think the canonical force is better. Canonical force, and this is dl by dr. That's equal to what? Okay. What is dl by dv? mv, there's nothing else. Very good. And what about dl by dr? mg and 2 times lambda. Newton's law, or in this case, Euler-Lagrange equation, right? Euler-Lagrange equation, which gives you the Newton's laws, Lagrange equation. So, yes.
We are writing.
Oh, sorry. Because it's in my head. So yeah. Because I have worked on this so many times that it always in my head it is T, yeah, sorry. Okay. Apologies, yeah, okay. So Euler-Lagrange equation is time derivative of this, right? Total time derivative of the canonical momentum is equal to the canonical force. So it is time derivative of mv, which is acceleration basically. Mass times acceleration is equal to mg plus 2 times lambda. Right? But we know this is Newton's law. We know that ma is equal to mg plus t. So at this point, I can identify the tension. Right. This immediately tells me that this is equal to force of tension. So T is equal to 2 times lambda. So from now on, they will write T plus 2 times lambda as T. Okay. So now we have a little more sophistication than the simple Lagrangians that we do. We can deal with non-conservative forces. How you accommodate with it is put a vector, Lagrange multiplier, gradient, and the constraint equation. Usually the hardest thing is to recognize the constraint equation. You should know which varies the constraint. That's the hardest part typically. Once you have this, then you just go through it. Okay, in your homework, there are some 3 examples. One is on the wheel, the other is the Atwood's machine. Like in an Atwood's machine, right? This is the Atwood machine, familiar? M1, M2,
Oh, yeah,
right? What's the constraint?
would be they're both M1 and M2 are connected.
They're connected, put an equation to it. Give me an equation of the constraint. Huh?
Tension.
No, I want a constraint equation. Some variables which move, they should be forced. There's a connection between one and the other.
This is same thing.
No, that's a force, right? That's not an equation of a constraint. That's a force that you're using the physics.
Yeah.
But T1 is equal to T2 because of what? Or let me put it like this, let me say it better, like look for dynamics. Constraint has to do with dynamics, right? This accelerates 2, right? Acceleration 2, acceleration 1. Which one is larger? A2 is larger or A1 is larger? It's a trick question.
A2
A2 should be large.
Huh?
It is going down. A2 should be large. Yeah. Oh,
It's a trick question.
A1 should be large.
Okay, think and tell me. It's a trick
I
question.
think one because it's going up. Maybe
I
10.
think, since I'm telling
would
you,
be greater
Think.
to
my,
Say
force of gravity. I think,
because it's a system, right? So if it is going down, then it should come up the same.
very good.
Yeah.
Right? It's a connected. If I'm moving, is my head accelerating faster or my tail is accelerating faster? I don't have tail, like legs are accelerating faster, right? Both are the same. I'm connected. If M2 moves 3 meters, M1 has to move up 3 meters. It's up and down though. So it was a trick question that I was making you think in the wrong direction, right? But they're connected, right? So that's the constraint. That's dynamics is the constraint. So what's the constraint? If this is length y1, y2, y1 plus y2 is L. That's the constraint. If I take a derivative of this, y1 dot plus y2 dot is equal to 0. y1 double dot plus y2 double dot is equal to 0. Acceleration a1 is equal to minus acceleration a2. Right? That's the relation. One goes up, one goes down. So this equation is what will go in here. Okay. In your homework, you do this problem. This is the primary thing. And that is what is causing the tension. So that's related to the force of tension is doing that job of making sure that y1 and y2 are exactly the same. So whenever you're doing force equations, you will say these are ropes are inextensible. And if the source, if the force is elastic by, oh, sorry, if the rope is elastic by any chance, then these equations don't work. So in your experiment, you have to make sure that these things work. Okay. So let's proceed and let me do a few more things. Now you're ready for the homework, by the way. So you should be able to finish the homework before the spring break so that you have your spring break clear. Right. Okay, but that's your Lagrangian. That's canonical momentum, canonical force, and that's your Newton's law. If you want Euler-Lagrange equation, usually gives you the Newton equation. Let me use this to replace this and write this as T. That's my Lagrangian. Usually the step afterwards is, especially because quantum mechanics, we don't know how to work on quantum mechanics other than using the Hamiltonian. We don't know how to work on quantum mechanics like Lagrangian if you want. So usually Hamiltonian is how you begin with. So you want to switch over to the Hamiltonian somehow. Usually quantum mechanics is interesting. So you want to go from Hamiltonian, Lagrangian to the Hamiltonian, and Hamiltonian is for a given coordinate. So here there is one generalized coordinate, right? R is the only generalized coordinate. V is related to that. V is not independent. So maybe I should say that this is generalized coordinate. And this is not independent. This is important, not independent. For example, the action that I write will be dependent only on R. I vary only R. I get only one equation. I vary R, I get one equation. Hamiltonian, on the other hand, has two independent variables. It's R and P. What is P? P is this quantity in here. The canonical momentum gives you the P. The moment I write down the Lagrangian, I get my P.
Wait, so going backward, the Lagrangian generalized coordinate. V is not independent.
V, it is better to say that this is R dot. The derivative of the Lagrangian with the derivative of the generalized coordinate defines the momentum associated with this coordinate. If there are two generalized coordinates, there will be two generalized momentums. Okay, so like double pendulum is a classic example. There will be two angles there. For each angle, you will get a canonical momentum or a generalized, canonical momentum associated with it. Okay. So if it's a double pendulum, there will be two theta 1, theta 2, and now there is a momentum associated with theta 1, momentum associated with the theta 2. So now there are four independent variables. So maybe I should point this out. These two are independent. That means if I were to use action principle, if you remember, there was a homework where we took the variation of the action with respect to the variables. When we were doing Hamiltonian, we did two variations. Lagrangian, there is only one variation. Hamiltonian, two, and the Schwingerian, when you write the Schwingerian, there are three variations you make: velocity, position, and momentum. So there are three independent equations you get. So Hamiltonian is defined as velocity dotted with P minus the Lagrangian. Lagrangian already has R and V in it, and that is T also. Maybe I should, at least in this case, write T. But in this problem, we don't have any time dependence. So that's. It turns out that the way this is defined, it will never have the velocity dependence in here. Hamiltonian is always independent of the velocity. So let's write this down. So H is equal to V
dotted with P. Let me replace V with P here. In this problem, it is easier, right? So it is P over M. As far as possible, quickly replace V with P's. Why did I do that? Because it's P is equal to MV, right? As quickly as possible do it, and don't be biased with the idea that momentum is MV. Most often it's not. So minus of half MV square, again, replace M and P over M dotted with P over M. Whenever possible, try to replace it out, and it's plus MGR, so it is minus MG dotted with R and minus P. Oh. Okay. That's your Hamiltonian. Let's simplify this a bit. So these two gets so it is P squared. Write this out as P dotted with P over 2M minus MG dotted with R minus extension. Right, that's your Hamiltonian. Hamiltonian leads to Hamiltonian equations of motion. Hamiltonian immediately leads to Hamiltonian equations of motion. And what are Hamiltonian equations of motion? There are two variables. So we ask about what is the derivative with time and what is the total derivative with the second generalized variable. That's the momentum, position and momentum. And Hamiltonian equations of motion tells us this in terms of the Hamiltonian. This is the derivative of the Hamiltonian with respect to momentum. And this is the derivative of the Hamiltonian with respect to the position, sort of opposite to each other. And there is a negative sign associated with that. Okay. It's often confusing as to where the negative sign sits in. Think this is force, right? dP by dt force. Hamiltonian is energy typically. So force is negative gradient of energy. You remember that from other contexts. So negative sign is with P always, but you will realize that it gets confusing quickly. But we can evaluate that. Hamiltonian partial derivative of that, that is P appears only in here. So it is P over M. And negative gradient of Hamiltonian. So this is negative. So it is mg plus T. Again, you get the same equation, except when you write it in terms of Hamiltonian, it is in two pieces, right? Momentum, say, rate of change of momentum are the sum of forces, and the momentum itself is related to the velocity. Right? So this implies that P is equal to mass times. Again, whenever you're working in Hamiltonian, it's good not to write velocity because dr by dt is in principle independent of velocity, but at some level you stop. It's mainly the action principle. Whenever you're working with action principle, it is okay to do that. Velocity and dr by dt being replaced. Numerically, it is the same. That's the language. Otherwise, it is not. Okay, so that's one thing. And usually we are also talking about once you have your Hamiltonian, you will often see the expression that is angular momentum conserved or not. And we want to start talking about the situation. We will talk about symmetries and so on. But in the last 10 minutes I have, let me try to show that angular momentum. So what is angular momentum in terms of momentum? Huh? MV dot or no, right? The vector. That's it. No.
MV are not the cross out plus.
It's
B.
cross, right? It has to be vector. But it is MV cross R or is it R cross MV?
R cross MV.
R cross MV, right? R. So think of circle, right? This is velocity. That's your R's, right? R cross MV will bring the angular momentum out. So angular momentum, right-handedness requires that it is R cross. Then that's a definition. So that's R cross MV. And basically it's R cross P in this case, right? That's right, that's MV, that's right, R cross P in our system. What about dL by dt? If this is equal to 0, what does that mean? It is conserved, that means it is not changing with the system. That means that notice L is coming out of the board for this problem. Once you start your system, you can do whatever you want, but that vector cannot change direction. Like Kepler problem is a popular classic example where the angular momentum is conserved. You can change your R, which is not obvious if you notice. In circle, it comes out to be obvious. Notice, so this is where it sits, right? So that's your R. And that's your velocity V. Right? Velocity is always tangential to the trajectory, right? R cross MV has to remain the same. That means basically what you're saying is that it has to stay in the plane. Like once the motion begins, it cannot leave the plane. And there are distances that is decided based on that. But first thing you say is that it has to be in the plane of R and V. Because the cross product has to remain exactly the same. But then since these distances are not the same, it has to satisfy some constraint. What is the constraint it satisfies? What did Kepler tell us? Same area, very good. Kepler's second law tells us that if you were to have area swept by a planet when it goes from here to there, in 1 second or let's say 1 month is exactly the same with respect to the sun. So when it is, since this area is longer, if you think of a very elongated ellipse, like in Earth, this is not very relevant. If you take Pluto, its eccentricity is very large. So this is having a very large area. As you get closer, it has to go for a longer duration of time. So the only way it can happen is that it has to go faster here. Right. So if the area has to be maintained, so it will go faster in here. So Kepler's second law immediately tells you these relations. So you will show this in your homework, part of your home, and the same thing holds here, by the way. Right? Angular momentum is conserved in this scenario. It's not angular momentum as a whole is conserved. It is the angular momentum along the axis, or in this case, G, right? G decides here. So angular momentum in the direction of G will be conserved, right? So you will show that. But let's say in general what happens. So this is, if whenever I'm taking the derivative, there are two places. So this is dr by dt crossed with velocity. But I can do the second also, right? Plus r crossed with acceleration, or dv by dt. What is the cross product of dr by dt and momentum? Zero. Why is that good? Because this is velocity itself. Velocity crossed with cross product of the same vector is 0. So that's 0. And this is nothing but force, right? Total force, R cross MA. You want, that's R cross MA. So you want In general, dl by dt. If, right? So if P is equal to mv, it is equal to R crossed with ma, right? What is the central force, by the way? Based on your earlier exposure, I haven't used this in this class here. Are you familiar with the idea of a central force? There is a class of forces which are called central forces. Usually forces have position dependence, like think of gravity, right? Gravity is G m1, m2 over distance square, right? It doesn't depend on the vector nature of R, it depends on the magnitude of the R. And this is vector R, direction itself, right? And that's the gravitational. This is central force, where it depends only on the direction R hat and mainly the magnitude. The magnitude of the force should be just R dependent. So that's a central force. In this scenario, if you were to put this here, what can you, so for central forces. So what is the central force? Maybe I should say F is equal to some R hat times F of R. Reasonable? So it depends, the magnitude is completely decided by the length of the vector and the direction is R hat. So that's a definition of it, central force. So for central force, like a planetary motion is governed by a central force, what can you say about angular momentum? Conservation. So this will be R vector R crossed with R hat. Because there's only one force, ma is equal to that force. And that's equal to F of R. What is that equal to? Zero, right? Direction is the same, sin theta is equal to 0, that's 0. So angular momentum is conserved for whenever it is a central force. We were doing the problem of a spherical pendulum. Are the forces central in that? Mg and P, they are not central, right? So dl by dt for the spherical pendulum. So for spherical pendulum, is equal to R crossed with MA, which is mg plus force of tension. That's not central in our case. But now one can do, okay, this is not conserved. So you say that angular momentum is not conserved. For the spherical pendulum, angular momentum is not conserved. But you could ask, is a component of angular momentum conserved? Right? Is the angular momentum conserved in a certain direction? So you ask, so this means, this implies angular momentum is not conserved. Not conserved. Conserved. Or, but we ask a new question now. Okay, that's not conserved. What about L in the direction of G? Component of L, dot product is typically the angle. This is also the projection of L in the direction of G. Right? That's the dot product. That's what it means. So this is equal to G is a constant. So we just have to worry about this is nothing but G dotted with the L by dt. Oh, by the way, what is r cross t? But the spherical pendulum? If I measure it from the center here. R is this way. T is that way, is 0, but R cross T for the case of pendulum is again 0. T dotted with L, help me, the L by dt was R cross, right? So it is R cross mg plus G dotted with R cross T. This was equal to 0, we are here already. Is this equal to? What is G dotted with R cross mg? 0 again, because this is perpendicular to this, so this is also 0. So that means this is conserved. So the component of the angular momentum in the direction of the axis, that is when the pendulum is rotating around, it has to remain the same. Angular momentum has to remain the same. You will see more of this in your homework, and I'll stop here.